Okay, in this section we are going to have a look at workload scheduling. So workload scheduling is quite an important concept within OpenMP, with any parallel system, and it basically determines how the processing is split amongst the threads. So we've seen examples so far where we've taken a for loop of a set number of iterations, and we've seen that basically the OpenMP system has divided the number of iterations by the number of available processors in order to determine how many do what. So for example, on this machine, 10 processors available, we have a loop of 20. Each thread in the team will get 2 iterations to complete. So this is fair in one way. Everyone has the same number of iterations to complete, and it is what we refer to as static scheduling. So in this mode, the OpenMP system will determine what is the fairest, i.e. divided number of tasks by the number of available processors and execute them. Where this gets a little bit more interesting is when we get to real world problems where each execution can require a different amount of work or a different amount of time. So a way of thinking about this is if I said I have 20 tasks to do and I have 10 people to do them for me, one option is, okay, everyone gets 2 tasks. But if all the tasks aren't equal, if some tasks perhaps are 2 or 3 times as onerous, is it still fair or sensible to just divide them up that way? Because one of our workers could well get 2 very onerous tasks, another one of our workers gets 2 very easy tasks, and yes, okay, that's great for one, not so good for the other, but it's not exactly the most efficient use of time. And when it comes to thinking about threads, what we're interested in is not necessarily how hard they're working, but trying to finish as quickly as possible. So if we have some tasks which take a lot longer, and we end up possibly giving 2 of those to one thread of execution, then our overall execution time is going to be longer than if perhaps we could split those up a little bit. So let's have a look then at some of the controls. Now there's an awful lot of documentation available to look at the different types of workload scheduling available. And we're going to have a look at the 2 most common that we would use. So static, which we've already seen, and then dynamic. So let's start with static. So here is a program to sort of attempt to show a little bit of this working. What have we got? Well, we begin, we initialize a random number, we move into a parallel region, and we initialize a sleep value as a random number between 0 and 2 million. 200. Sorry, yeah, it's 2 million, yes. So we're dealing with milliseconds, so this is a sleep of anywhere from 0 to 2 seconds. We say, hello from thread whatever, I will sleep for this number. And what we're doing with this is we're creating an artificial delay to allow us to see the difference when threads sleep a different length of time. We're then creating a for within our parallel region, not parallel for because we're already in a parallel region, so we're just using our existing team in order to do this. We're doing 20 iterations. Each one of those we're sleeping for the set period of time, and then we're printing some information. Thread is this, the number is this, slept for that long, and then finally we're printing when all threads finish out the bottom. And then the end of our parallel region as well. So let's have a look at what that looks like. I'll just pull this up so we can see it running. So you can see that we start off and our threads are all sleeping for different amounts of time. We go through thread 0, etc. Smaller sleep there. And then we go through our steps of iteration. Now, because the thread sleeps for a certain amount of time per iteration, some threads are going to take a lot longer to do their 2 iterations than other ones. I mean, the longest amount of time looks like thread 2 there, or in fact thread 4, I think. So that's going to sleep for 1.5 seconds, and you can see that thread 4 is going through and being quite slow in terms of its execution. So running this again, we can see that we're going through, but everything is getting 2 pieces of work. Once a thread has finished its piece of work, it cannot do anything else until all threads are finished at the point where we've finished the for loop and we have an implicit barrier there. We can see this even more obviously if we introduce a particularly high delay for one of our threads. So let's go here, we're saying we set the sleep as a random number, but let's say if OMP get thread num 2. So thread 2, we're then going to say that sleep equals, let's give this 5 seconds. So thread 2 has now been interfered with and is sleeping for longer. And the other thing we're going to do is we're just going to take this, instead of 20, we'll take this up to 30. So everyone gets 3 pieces of work. We run this, we can see all of these other threads are going through. Carrying on to work, there's thread 2 coming out, I equals 6. It's though then sleeping for 5 seconds, 7, and presumably 8. So when we time this, the other threads are working away there, but our execution time is pretty universally going to be 3 times the longest sleep, in this case thread 2. So our execution time is going to be somewhere around 15 seconds. Now clearly that is not the most efficient way of working. We have other executions, so execution 5, 7 and 8, in thread 2, 6, 7 and 8 are being performed, and we cannot move on, we cannot end, because while 6 is going on that we know is going to take a longer time than the other ones, we can't even start 7 and 8 until that is finished. So this is exactly the same as manually specifying scheduling static. And static scheduling, as mentioned, is just, schedule. Static scheduling is literally take the workspace and divide it by the number of threads available. So what are other options to do that? Well, static scheduling has the advantage that it's very, very easy to calculate. It's the simplest thing, we can understand it, we divide the work up, and it's a very low overhead in terms of the actual requirements to run it. Another type of scheduling, and as I say, there are various other ones, automatic, guided, runtime adaptation, is dynamic. Now with dynamic scheduling, we can give it what we call an optional chunk size, and I'll talk about that in a minute. What this is doing is this is making a decision on how to distribute the pieces of work amongst the available threads. So by default, the chunk size will be 1. Let's have a look at what that looks like at execution. So remember, we were getting 15 seconds before. Here we go through, and we're still waiting at this point for thread 2, but thread 2, sleeping for 5 seconds, has only got 1 piece of work to do. So what's happening in the background is there is ID 6. Remember before it had 6, 7 and 8. You can see that 7 has been given to thread 7. 8 has been given to thread 6. What happens with dynamic scheduling is there is a queue. So at the start we have 30 now pieces of work available. Our chunk size is 1 by default. As I say, we'll come back to have a look at that in a second. It means that every free member in the thread team, and at the start there are 10 and they are all free because they've just been created, takes 1 piece of work. When they then finish that piece of work, they return to the start of the queue, and they take also the next item in the queue, not the start of the queue. They return to the queue and they take the next item in the queue. So if we have pieces of work which for whatever reason take longer, and here we've artificially created it so that every time thread 2 does anything it takes 5 seconds, it goes through and it's executed incredibly quickly. Now actually everything has reasonable same amount of sleep. The reason why is because we're randomizing using time, so they're all fairly similar, because I think they're probably randomized at the same time, and then being random isn't thread safe. But let's put another artificial thing in. So we've artificially given thread 2 a long sleep. Let's give thread 3 an incredibly short sleep, so 5 millionths of a second. So what that means is that every execution of thread 3 is going to be a lot quicker than the other ones. So let's compile this and let's have a look. Okay. And what we see here is, wait for this to finish, again, 5 seconds of execution. Let's have a look logically through it. So all these threads, everything apart from thread 2 and 3, have a random sleep, and that varies from 63,000th of a millionth of a second all the way up to, what's that, 1.5 seconds. Thread 2 is 5 seconds, and thread 3 is 5 millionths of a second. So everything executed by thread 3 happens very quickly. Thread 2 takes a lot longer. So the program starts. All of the team are available. Everyone gets one piece of work. What then starts to happen is that these threads, everything apart from 2 and 3, we know a random amount of time, and they're all taking a longer time than 3. So they are going through and they are waiting to come out the other end. Meanwhile, 3, because it's finishing its work so quickly, the first 10 pieces of work are given to the threads. It has finished its work before the other 9 are completed. So it will then take 10, 11, 12, 13, because it's returning to the queue while all of these are still sleeping. Now you can see that a bit clearer if we swap the order of this, and instead of printing afterwards, we print before we sleep. So we print as soon as work begins, not when work ends. So again, we see exactly the same thing. And if we go up to the start, you'll see here, there we go, we're getting all the hellos, right? And we're starting to see work being allocated to thread 1, thread 9, thread 6, thread 7, thread 2, thread 0, piece of work to thread 3, piece of work to thread 8. At this point, everything apart from thread 3 is still working because it's sleeping for a period of time. Thread 3 finishes and just comes straight back and takes all of the other pieces of work. And overall, our execution time now is optimized. Just to return to something I mentioned earlier on, we talked about chunk size. So by default, chunk size, that is just the number of items, if it can, that it will take across the list. So currently we set that to dynamic, and without anything else, without any change of compiler options, etc., that is the equivalent of doing dynamic 1. So take a chunk size of 1. Take one item, work on it, and then come back and take another one item at a time. If we start to up this, then it makes it a little bit easier because we can take a couple of pieces at a time. The overhead becomes less, but of course potentially our efficiency becomes less. And in this example, by the time we've gone to schedule dynamic 3, we are effectively doing static scheduling. Everyone gets 3 pieces of work. Usually 1 is absolutely fine. In some cases where we're perhaps doing thousands and thousands of iterations, and it's less likely that they're going to be long, but some of them are, then a higher schedule, a higher chunk size is appropriate to make that more efficient. Now, as I mentioned, there are other types of scheduling available. So this is static and dynamic we've seen, and there are guided and auto and various other things which are discussed in the documentation, but this is the basic concept of workload scheduling. Take a set number of tasks, a set number of iterations. How do you divide them up amongst the available teams? Do you give everyone an equal amount, or do you attempt to give everyone an equal amount of work in terms of time?